This is the first video for the Annuities module, and in this video we're looking at sections A to D. To begin, let's look at our objectives. To understand the concept of annuity, to perform calculations involving annuity lump sums, to perform calculations involving annuity payments, to determine if an annuity is an annuity due or an ordinary annuity, and to do calculations on amortized loans. So what is an annuity? An annuity is a series of equal payments made at equal intervals of time. The payments may occur weekly, fortnightly, monthly, quarterly or yearly. Each payment is called the periodic payment, and the total time for which these payments are made is the term of the annuity. Examples of annuities include regular payments into savings accounts, superannuation funds, loan payments, periodic payments to a person from a retirement fund. An annuity is a special type of geometric series. So if you did the STSD module, you would have encountered annuities already. There are two types of annuities: ordinary annuities and annuities due. So let's start with ordinary annuities. An ordinary annuity is an annuity where the regular payment is made at the end of each payment period. Now let's look at the present value of an ordinary annuity. The present value of an ordinary annuity is the amount due at the commencement of the term and is equivalent to the sum of the present values of all the periodic payments. So what we're talking about here is we want to know how much we need at the beginning. Okay, so we want to know how much do we need to deposit in the beginning at this 0 point such that we can have regular payments. And these are the regular payments that you can see here coming back to the beginning, because we need to work out, well, we want to make these payments, how much do we have to put in now for the future? And the regular payments are represented here. Okay. So that's what I mean by the present value of an ordinary annuity is the amount due at the commencement of the term. Now converting each of those repayments into its present value and then summing the series gives this formula here. You do not need to remember these formulas, they will be provided. Now A is the present value of the ordinary annuity, R is the amount of each repayment, I is the interest rate per period, okay, notice per period, and N is the number of periods. So let's look at an example. What lump sum should be deposited today at 5% per annum compounded annually so that for the next 4 years withdrawals of $1,000 can be made? So you can see here I've already included the timeline. So we're looking at what we have here so that we can make these $1,000 payments each year. So how can I make these payments? What do I need to deposit now? Okay, so let's write down our information. We have our interest rate is 5% per annum, which is 0.05. Now it's compounded annually, so I can leave it as that 0.05. I don't need to divide by anything. We're looking at 4 years, so N is 4, and our repayments we want to be $1,000. So write out our formula. Once you've written out the formula, make sure you write it out properly. It's really disappointing when you write out the incorrect formula. Plug in what we've got. So we've got 1,000, 1 minus 1 plus 0.05 to the power of -4 all over 0.05. Plug that in your calculator, and I really recommend you use the brackets. Put the brackets where the brackets are in the formula so you're unlikely to make a mistake. And you get 3545.95. Finish with a therefore statement. So you've got $3,545.95 should be deposited today to enable withdrawals of $1,000 for the next 4 years. Now the periodic payment period, N, is not the same as the per annum nominal rate of the compound interest. Okay, so when it's not the same, you need to use I. So this is the same as what we did in finance. So if we have our yearly rate of 5%, but we're making payments quarterly, then we need to divide it by 4. Okay, so if the periodic payment period is not the same as the per annum nominal rate of compound interest, then I must be calculated just by dividing that rate by the number of periods. So let's look at another example. Mr. and Mrs. Lyons wish to invest in an annuity that will pay their daughter $1,000 a month for 4 years. What is the present value of the annuity? Present value, given that the current interest rates are 8% per annum. So you can see from the timeline here, I've abbreviated it because we've got 4 years, but we're paying monthly. We have to go 4 times 12, which is 48 months. And that's why you can see it going from 0 all the way up to 48. And we're making that $1,000 each time. So what we want to know is how much do we have to deposit here so that can happen. Okay, so when we're looking at I, our I is going to be that 8% divided by 12. Now, in the textbook, they actually use the decimal equivalent. I would leave it because it can't be reduced exactly. So what you go to is 0.08 over 12, which you can reduce, or you can just leave it like that. You're just throwing it into the formula anyway. Okay, so you can just leave it as 0.08 divided by 12. So let's go to our formula. We've got A equals R. Now note, in the textbook, the formula is written a different way. Now this is to show you that it doesn't matter if that R comes out the front or I put it all over. So what I mean by that is if I write out the formula like this, I can put that fraction all the way like that, or I can just put it just over the I. It means the same thing, so don't get caught up if you see it looking different ways. So from here, if we plug in our repayments, well, we want $1,000 per month, so that's 1,000. Then we have 1 minus 1 plus 0.08 over 12 to the power of negative 48 all over our 0.08 over 12. Okay, note that I have left that fraction. I don't want to keep approximating. Now when you plug in your calculator, be really careful. Again, you might want to, if you're going to use the formula this way, you need to remember that you've still got that bracket around all of that. So you're going to have to use brackets. Okay, so our answer ends up being $40,961.91. So therefore, you would need to invest $40,961.91 to get that regular $1,000 payment for 4 years per month. So finish that there. $40,961.91 needs to be invested now to provide a regular $1,000 monthly payment for 4 years. Now, Roger Little borrows $20,000 to buy a car. He wishes to make monthly payments for 4 years. The interest rate he is charged is 10.5% per annum. What is the size of each monthly repayment? So this is looking at finding R rather than finding A. Okay, and you can see my timeline here. I've got it up to 48 because it's 4 years, N is 4 years, but it's a monthly payment. So we need to go 4 times 12, which is 48 months. Again, our I is going to be our interest rate, our 10.5%, but that's per annum, so we need to divide it by 4. So our 10.5 as a decimal becomes 0.105 over 4. Now if you work that out in a calculator, you do get a decimal that you can write out. It's just 0.02645. It's not recurring, it doesn't go on forever. It's nice and easy decimal, so you don't have to leave it as a fraction. So you can see from my timeline that these payments are each coming down to here. So we end up with that $20,000, and we want to know what do we have to repay to have that $20,000 given to us at the beginning. So our normal formula is A equals R 1 minus 1 plus I to the negative N all over I. Now we want that R on its own, so we're technically dividing the A by all of this here. Okay, so we've got A over 1 minus 1 plus I to the negative n all over I equals R. So that I comes up to the top, we end up with AI all over 1 minus 1 plus I to the negative n equals R. Plug in what we've got, I'm going to put the R on that side so it makes it easier. Our amount is $20,000 over 1 minus 1 plus 0.02645 to the power of negative 48. Okay, let's look at another example. Roger Little borrows $20,000 to buy a car. He wishes to make monthly payments for 4 years. The interest rate is 10.5% per annum. What is the size of each monthly payment? So we're not looking for the amount that we want to put in. We know that we want $20,000 given to us. And that's represented on the timeline here. We want $20,000. So how are we going to repay that if I need to pay it back in 4 years? So what do these repayments need to be to do that? Now, we're making monthly payments, so our N is 4 times 12, which is 48. Our I is that 10.5 divided by 12. So 10.5 as a decimal is 0.1, sorry, because that's percent, 0.105 over 12. Now, if you put 0.105 divided by 12 on your calculator, you can you do get a nice decimal that you can write out, so it saves you using that fraction. It's 0.00875. You know that the amount you want is $20,000. So if we have our formula A equals R, 1 minus 1 plus I to the power of negative n all over I, we want this R to be on its own. You can substitute in now and then rearrange, or you can rearrange now, because you should be able to see, well, to get R on its own I just need to divide by all of this. I'm going to write it over here so I don't run out of room. So I end up with R equals A all over 1 minus 1 plus I to the negative n all over I. To do this division, that I comes up the top, so you end up with AI 1 minus 1 plus I to the negative n. Plug in what we've got, so we've got 20,000 times by 0.00875 all over 1 minus 1 plus 0.00875 to the power of negative 48. Now again, remember to use brackets. And what I mean by that is you want to divide the top by everything on the bottom, so you're going to need brackets on the outside when you plug it in into your calculator. You get $512.07. So finish with a therefore statement. So you've got Roger will pay $512.07 per month for 4 years. What now? There were 2 exercises in the textbook, ANNT-D1 and ANNT-D2. Remember to check your work. Remember that if you need to, go back over the videos. You don't need to memorize formulas, they will be provided.